We have mentioned previously that an ideal Carnot engine operates with maximum efficiency when its thermal process is reversible. However, irreversible processes like friction cause real engines to operate with less than maximum efficiency. In general, irreversible processes cause us to lose some, but not necessarily all, of the ability to perform work. This partial loss can be expressed in terms of a concept known as entropy. Again, we recall equation 15.4, which applies to a Carnot engine. We can rearrange this equation in the following way, which isolates the heat Q divided by the Kelvin temperature T. This quantity, Q over T, is known as the change in entropy delta S. In this expression, the temperature must be in kelvins, and the subscript R designates a reversible process. This equation applies to any process in which heat enters, a positive Q, or leaves, a negative Q, a system reversibly at a constant temperature. The equation above also shows that the SI unit of entropy is a joule per Kelvin. Entropy, like internal energy, is a function of the state of the system. In fact, only the state of the system determines the entropy S. Therefore, the change in entropy delta S is equal to the final state entropy minus the initial state entropy. We can now describe what happens to the entropy of a Carnot engine. As the engine operates, heat is extracted reversibly from the hot reservoir, which decreases its entropy. This corresponding change in entropy is given by the following, where the minus sign is needed to indicate a decrease in entropy. In contrast, the entropy of the cold reservoir increases by the following amount for the rejected heat that reversibly enters the cold reservoir at a constant temperature Tc. The total change in entropy is then given by the sum of these two changes. And since Qc over Tc is equal to Qh over Th by equation 15.4, the total entropy change is equal to 0. The fact that the total entropy change is 0 for a Carnot engine is a specific illustration of a more general result. It can be shown that for any reversible process, the total change in entropy of the universe is equal to 0. The word universe takes into account the change in entropy in all parts of the system and its environment. Thus, reversible processes do not alter the total entropy of the universe. The entropy of one part of the universe may change due to a reversible process, but this means that the entropy of another part must change in the opposite way by the same amount. Now, if the process is irreversible, then this expression for delta S does not apply directly. However, if a system changes irreversibly, we can use this expression to calculate delta S indirectly. Imagine a hypothetical reversible process that causes the system to change between the same initial and final states. The value obtained for delta S also applies to an irreversible process, since only the nature of the initial and final states and not the path between them determines delta S. While reversible processes do not change the total entropy of the universe, an irreversible process will always increase the universe's total entropy. Therefore, the entropy of the universe is continually increasing. In fact, entropy is sometimes called time's arrow. This is a general consequence of the second law of thermodynamics, and we can restate the second law in terms of entropy. It should be noted that whenever an irreversible process increases the entropy of the universe, the energy available to do work decreases. This leads to the following general result. The energy that becomes unavailable for doing work is equal to the temperature T sub 0 times the change in entropy of the universe, where T sub 0 is the Kelvin temperature of the coldest heat reservoir. Entropy can be interpreted in terms of order and disorder. As an example, consider a solid block of ice, with its H2O molecules held rigidly in place in a highly structured and ordered arrangement. In contrast, once the ice melts, the liquid water molecules are in a much more disordered and unorganized arrangement. Heat is required to melt the ice and produce the disorder. Moreover, heat flow into a system increases the entropy of the system according to equation 15.18. In general, we associate an increase in entropy with an increase in disorder. The demolition of a building demonstrates how an order to disorder change leads to an increase in entropy. Before the demolition, the building is in a highly ordered, low entropy state, and after, it becomes a disordered state of high entropy. In the next and final section of this chapter, we will introduce the third and final law of thermodynamics.